Many types of sensors, and actuators too, employ the principle of electromagnetic induction. One aspect of this is that a changing electric field generates a magnetic field, and conversely, a changing magnetic field generates an electric field. These two facts make sense because both types of fields are simply different aspects of the same thing, electromagnetism. The presence of an electric field causes an EMF, an electromotive force, a voltage that generates current. And this is often the basic principle that sensors use, while a magnetic field can be used to generate a force, and this is often the principle that's used by actuators. One reason this property is so nice is because it's non-contact, and this will become more clear, the usefulness will become more clear shortly as we discuss a few specific examples. So one type of sensor that employs electromagnetic induction is the resolver. A resolver can be used to measure angular position. And the way that it works is that you have some carrier voltage, some input voltage that's an AC signal, an alternating current. And that changing electric field creates a magnetic field, and that magnetic field then induces current in a rotor. And so this is in essence a transformer. This is how a transformer works. This AC current, this alternating current, creates a magnetic field, and that changing magnetic field creates a current in the pickup. And so we generate some current in this pickup coil that's attached to the rotor, for example, in the middle of a motor. And then this current induces another magnetic field which induces current in these two pickup coils, one called the cosine winding and one called the sine winding, and these are fixed on the stator of the motor. The fact that these two pickup coils are offset causes the current that they generate to change differently as the rotor moves. And in particular, the relative magnitudes of the currents in these two outputs can be used to determine the position of this rotor throughout its 360 degrees of motion. Here's an example where we can see how the non-contact aspect of electromagnetic induction is nice. We have this rotor in the middle of a motor and it's spinning, and we're able to sort of get current to it without a physical connection. Another type of sensor that works on this same principle is called a linear variable differential transformer, an LVDT. This type of sensor measures translational displacement. It's similar to the resolver in that the source is an alternating current, and so we have this sort of primary coil here. So this alternating current creates a changing magnetic field, and that magnetic field then induces current in these two pickup coils. So we call this the primary, and it induces voltage or current in these two secondary coils. As this metal rod, of some sort of ferrous material in the core moves, is displaced, it affects the way that current is induced in these two secondary coils. In particular, the amplitude of the output voltage is proportional to the position of this core, and that gives a means for detecting displacement. Furthermore, the phase of the output voltage changes direction whether the core is moving one direction or the other direction. Another type of sensor that doesn't work on quite the same principle as a resolver or an LVDT is called a Hall effect sensor. So this is a Hall effect sensor, and it can be used to measure the strength of a magnetic field. And since current generates a magnetic field, it can be used as a sensor. It can also be used to measure speed or position. So for example, you can imagine this gear is spinning, and as these teeth pass the Hall effect sensor, the teeth sort of change the magnetic field, and that change in magnetic field can be detected by this sensor. So in essence, you can get these pulses every time a tooth passes by. And so this can be used, to measure speed or position, for example, for crankshaft timing or for anti-lock brake control. And so if you've seen inside a vehicle, you can find a sort of gear like this in sort of the hub of a wheel, and what it's basically doing is it's a wheel speed sensor. It's measuring how quickly this gear in the hub is rotating. For those of you that do any sort of cycling, and you have these little computers on your bike that you can use to measure your speed or how far you've traveled, the way that it works is, in essence, you put a magnet on your spoke, and you put a pickup on the fork of your bike. And so every time this magnet passes by the pickup, passes by the forks, you generate a pulse using a Hall effect sensor, and it counts these pulses to get displacement, and it times the frequency of the pulses to get your speed. Another type of component that can be used as a sensor is an electric generator. And so this is a picture of a generator. It has the same structure as a motor. With a motor, you apply a voltage to the system to generate motion. With a generator, it works in the opposite way. Motion generates a current, output. And so this generator can be used as a sensor because the voltage it generates, the EMF it generates, indicates the speed of the generator. At this point, I won't get into the principles based on which this works, but this is something we'll come back to later. It's also worth noting at this point that a generator, for example, can be used to charge a battery. So if the vehicle, you want to brake the vehicle, you want to slow the vehicle down, you can use the vehicle to turn this generator, thereby slowing the vehicle down and generating electricity.